Welcome to this course on Verilog RTL design by example. I am DS Harish Ram and my course assistant is A. Jayanth Balaji. Both of us belong to the Computing, Hardware Systems and Architectures group of the Electronics and Communication Engineering Department of Amrita School of Engineering, Amrita University, Coimbatore. In this introductory lecture on HDLs, we will provide an overview of hardware description languages. We will start with a recap of VLSI design flow. Then we will examine the evolution of digital design over the years. We will look at the differences between hardware description languages and high-level programming languages. The concept of delta cycles, which forms the heart of hardware description language-based simulation, will be taken up. Finally, we will wrap up this lecture with an example Verilog module and its test bench. Now, to put things in perspective, we will briefly look at some of the important phases of VLSI design. Of course, this flowchart that I have shown here is by no means exhaustive. For a detailed treatment on the VLSI design flow, I refer the student to some standard textbooks in VLSI design. As you may be aware, a major part of the VLSI design process happens in software. In fact, this trait has facilitated the segregation of the design process from the fabrication process. In the early days of chip making, you might have seen that the VLSI design activity was confined to the design houses of the chip makers themselves. But with the advancement in desktop computing technology and with the advent of very powerful EDA tools from companies like Synopsys and Cadence, the process of design got completely segregated from the process of fabrication. So, in the late 80s and early 90s, this heralded a new era where a lot of design houses were started in countries like India, which didn't have their own foundries. Now, just like any other process flow, the VLSI design flow also starts with a system specification. Typically, the system specification is spelled out in a document called the SRS, which probably those who are working in the software industry or in the VLSI industry are aware of. So, as far as a chip is concerned, the system specification primarily consists of the mechanical specifications, the electrical specifications, and the functional specifications. So, the mechanical specifications pertain to the dimensions and the packaging and so on and so forth, whereas the electrical specification deals with the type of interface voltages that the chip is supposed to support, and also the drive current that each pin is supposed to handle, and also the power supplies that are typically going to be used by the chip. And as far as the functional specifications are concerned, of course, it encompasses the whole functionality of the chip. And typically it is specified by some high-level language in an object-oriented fashion. For example, if we are specifying the functionality of a microprocessor, this is usually done using transaction-level models, transaction-level object-oriented models. So after the system specification comes the high-level architecturing. So if you consider the design of a processor, typically the high-level architecture consists of the decisions regarding the instruction set architecture that the processor is supposed to have, and also the type of CPU it is supposed to have. For example, you can have a choice between accumulator-based CPU and a register file-based CPU. And the type of arithmetic that the chip is supposed to, the processor is supposed to support. So if you are designing a digital signal processor, for example, you need to have very powerful arithmetic blocks. Whereas if you are doing a general purpose processor, the arithmetic is not going to be so critical. So all these decisions regarding the implementation of each subsystem in the design are taken at the architecturing level. And once the architecture is ready, we go to the next stage where each subsystem is designed. And this is where HDL comes into the picture. So each subsystem in the architecture is designed and modeled using hardware description languages like Verilog and VHDL. And for modeling these systems, we have to first represent the design at a level of abstraction which is called the register transfer level, or RTL. So we will be having a separate lecture where the basic concepts regarding RTL will be discussed. So basically, as of now, it is sufficient to understand that the subsystems will be specified at the RTL level of abstraction, and they will be modeled using hardware description languages such as Verilog. And once the HDL modeling stage is over, the designs are synthesized using a synthesis software. And the outcome of the synthesis process will be a netlist which will contain all the gate level descriptions, all the gate level implementations of the design. And of course, there are a lot of subphases in the synthesis process, like the generic synthesis into a generic netlist, and the mapping process where the gates will be mapped onto the gates which are available in a library. So after the synthesis process, we go to what is called the backend. So the flows, that is starting from the system specification down up to the logic synthesis stage, is said to be making up the front end part of the VLSI design flow. And once the circuit is synthesized into a gate level netlist, then the backend process starts. And in the backend, we start with the circuit design where the schematic corresponding to each gate is designed, or rather it is extracted from each gate. And then we go to the physical design process where the blocks are placed and their interconnects are laid out. And once this process is complete, we go to the end of the design flow, which is usually called the tape out. So it must be remembered that all these phases, even though it is not shown in this diagram, all these phases are iterative. So each phase might undergo several iterations till the timing and area constraints imposed the design specifications are met. And the output of the design flow in the tape out phase will be all the files which contain the layout details of each layer in the design. That means there will be files corresponding to the diffusion layers, metal layers, the poly layers, and so on and so forth. So these files are represented in a standard format like GDS2 or CAF, and in this format they are handed over to the foundry for further processing and eventually being fabricated as a chip. Now the tape out process is called so because earlier these designs used to be stored in large magnetic tapes. So the final outcome of the design, the layout, used to be stored in such magnetic tapes, and therefore the terminology that was employed in those days was tape out, and it is still being retained even now. So this sums up the various phases involved in VLSI design flow, and we can see that in the front end stage, which consists of system specific high level architecturing, RTL design, and logic synthesis, HDLs are used in almost all the phases. So that brings out the importance of hardware description languages in modern design flow. Digital design has evolved by leaps and bounds in keeping pace with the Moore's law, which says that the number of components, the number of transistors in an integrated circuit will double every 18 months. So the design process has also evolved to handle the increasing levels of complexity that are demanded by applications. So initially circuits used to be designed using discrete transistors. Then of course there was some degree of integration that was achieved in the 74XX ICs. So you had small scale integration in the form of gates, and some subsystems were introduced using MSI ICs. But we could see that the design effort involved in using these chips as building blocks in digital designs was considerable, because there was no means of automating the design process. Designers had to represent the specifications in the form of a truth table, and they had to manually develop the Boolean expressions for the truth tables, and finally they had to implement the truth table using gate level circuits. And the circuits had to be rigged up in PCBs or wired in boards with wired interconnects. So there was a lot of scope for implementation bugs because of the high component counts. Therefore the reliability used to get affected a lot, and there was no debugging technique available. The circuits had to be debugged manually, and any bug that was found during fabrication resulted in high re-engineering costs. Then to handle increasing levels of complexity, the microprocessors were developed in the early 70s. We had the early generation microprocessors from Intel and Verilog. So these processors were able to accommodate a considerable level of complexity, and they also had the advantage that they were programmable. So this resulted in the component count in the PCBs getting considerably reduced, but still the glue logic that were used for interfacing the microprocessors with the peripherals like the memories and IO chips and other circuitry was considerable. So the glue logic themselves were again implemented using TTL ICs, and this resulted in high design effort. So even though there was some reduction in the component count, the design effort was still considerable. Some limited effort towards handling the complexity of glue logic was made in the development of programmable devices like PLAs and PALs. These were essentially arrays of AND and OR gates, and they were able to reduce the component count in microprocessor based systems to some extent. But still the design process was basically dependent on specifying the design at the Boolean equation level. So the design effort was not reduced significantly by using these devices, nor were they able to implement very complex systems. The next stage in the development of digital systems was in the advent of ASICs. Initially we had microprocessors, as I had mentioned earlier, which were accommodating a high level of complexity. Later on, chips which catered to specific applications were developed, and these were classified as application specific integrated circuits or ASICs. And then we had the field programmable gate arrays, which were programmable hardware that could be configured to implement any level of any functionality. So both the ASICs and FPGAs had massive levels of integration, and over the years they matured into what is called systems on chip, where there were several processors. You had a general purpose processor, and you had a DSP, and you had dedicated graphic accelerators, and you had a lot of interfaces. So these were called, and of course there was a considerable amount of software. You had even stacks, software stacks that were implemented. So these were very complex systems on chip. So the increasing levels of complexity necessitated the specification of the design at a much higher level of abstraction than the Boolean level. There was a pressing need for tools which could represent a design at the behavioral level. So this was the starting point for the use of hardware description languages in the digital design process. And now we have reached a stage where there are tools available which can directly translate an algorithmic description in MATLAB or C into an equivalent HDL file, which can be eventually synthesized into a target library. So we have tools like the Xilinx system generator and Catapult and Handle C from Mentor Graphics, which are capable of translating or synthesizing high-level descriptions in the algorithms to an equivalent HDL file. VHDL and Verilog are the most popular hardware description languages currently being used by designers worldwide. VHDL stands for Very High Speed Integrated Circuit Hardware Description Language, and it was developed by the US Department of Defense. Verilog was developed by Gateway Design Automation based in Massachusetts, USA. These languages were initially developed for logic simulation of boards which had digital ICs. The main objective was to detect functional bugs which otherwise had to be detected by rigging up these circuits on PCBs. This was a very cumbersome process, and there was no guarantee that all the bugs could be detected by actually testing the circuit physically on the PCB. Later on, these languages came to be adapted for synthesis. That is, software tools were developed which could parse the HDL codes and generate gate level netlists which could implement the functionality specified in the HDL code. The main advantage of these languages, the hardware description languages, is that they can model digital systems at different levels of abstraction, like the structural level, the behavioral level, the RTL, and so on. Of course, we will be having a separate session on modeling styles in the subsequent lectures. An important aspect in which HDLs differ from high-level languages is in their ability to model concurrency and delays. The following slides will elaborate on what exactly concurrency means. The ability of these languages to represent design specifications at the behavioral level of abstraction considerably reduces design effort. And that's one main reason why these languages are very widely used in VLSI design flow. To illustrate what exactly is meant by concurrency, I have shown two fragments of Verilog code which represent the same gate level circuit that is shown on the right. Now, the order in which the statements are written is different in the two code fragments. Nevertheless, they represent the same gate level circuit. It's basically a two-level circuit with the first level consisting of an OR gate and an AND gate, and the second level consisting of an XOR gate. So in the first fragment of code, you can see that the XOR gate appears first, whereas in the second fragment it appears second. But irrespective of the order, the same circuit is synthesized. So that's why we call these statements as concurrent statements. So eventually, when the circuit is simulated or synthesized, the same circuit will be inferred irrespective of the order in which the statements are represented. Now, the property of concurrency is achieved by means of a very powerful computational technique which is implemented using what is called the delta cycle. The idea of delta cycle, which forms the heart of HDL simulation, is illustrated in this slide. We shall use the same code fragment that was shown in the previous example. Now let us assume that there is a test bench wherein all the signals in this code fragment are initialized to 0 at simulation time 0. Now these HDL simulators, they evaluate the logic values of the signals based on either time steps or whenever there is an event in one of the signals. So in this example, let us assume that there is a signal event in the signal B triggered by the test bench at simulation time 2 nanoseconds. Now the simulator finds that there are two signals which depend on the signal B, namely Y2 and Y1. Therefore, the event in the signal B now triggers a computational cycle which is called delta cycle, wherein the signals Y2 and Y1, which are dependent on B, are now evaluated and their values updated. Y2, which was initialized to 0, now is updated to logic 1, whereas the value of Y1 remains unchanged in this computational cycle. So at the end of the delta cycle 1, the value of Y2 is updated to 1 and Y1 remains at 0. Now the sequence of computations does not stop with the delta cycle 1. The reason is, due to the update in the value of Y2, now the signal Y3, which depends on Y2, has to be updated. Therefore, the change in the value of Y2 sets off another cycle of computation. So in this cycle of computation, which is delta cycle 2, the logic value of Y3 is evaluated, and it is found that Y3 now changes from its initial value of 0 to a value of logic 1. So in the same simulation time 2 nanoseconds, it is found that there are two computational delta cycles. Delta cycle 1, in which the signals Y2 and Y1 are updated, and delta cycle 2, in which the signal Y3 is updated. In general, whenever there is an event in one of the signals on the right hand side of the assignment statements, it can trigger off a series of computational cycles. Each computational cycle will be a delta cycle. Now this sequence of computation will stop only when all the signals on the right hand side have settled down. That means the values of all these signals are updated. So we can see that in a particular simulation time, there can be several delta cycles. Each delta cycle consisting of several signal evaluations and updates. So this forms the heart of HDL based simulation. The values of signals that are computed at different simulation times are dumped into a file which is called the value change dump. So this dump will be used by a waveform viewer to create a display of the signal levels at different simulation times. This is how an HDL simulator works, based on the signal values that are either forced through the option available in the tool, or the values assigned through a test bench. The HDL simulation setup will consist of two files, that is the module that is to be verified, which is usually referred to as the device under test or the DUT, and the test bench, which is another HDL file, or it can be in the same file also, which is another module that assigns test vectors to the DUT. So once the module and test bench are ready, these files are compiled. Compilation basically looks for the correctness of the syntax used in the code. Runtime issues like the range of values for a particular signal are not looked into during compilation. The next phase is called the load design phase, where the design is loaded into memory for simulation. Now in this phase, the linkage between different modules has to be correct. If a particular DUT is instantiated in a test bench, then all the ports, all the input and output ports of the DUT have to be properly mapped onto signals in the test bench. This will be illustrated in the example that follows. So this is something similar to linkage in software. If we are using functions in a particular piece of code, the function calls have to be properly linked to function declarations, or else this might signify a linkage error. Likewise, in HDL simulation, the linkage between different modules that are instantiated in a particular file will be verified during the load design phase. Another step that is executed in this phase is called elaboration, where the initial values of all the signals used in the design are assigned. The next step is the simulation itself, where the simulator creates the simulation queues using the delta cycle computation, which was illustrated in the previous slide. The simulation time is advanced based on the events in the different signals as assigned in the test bench. The simulation process continues until there are no more events in any of the signals in the device under test, or until the duration that is specified by the designer. So there is an option for specifying the duration of simulation. So in either of these cases, the simulator stops. A structural Verilog code for a half adder is shown here. Structural modeling is analogous to realization of digital circuits using TTL ICs. So we use primitives for the different gates that are used in the circuit. The first step is, of course, definition of the module itself. So in the module definition, we assign some module name and we define the input and output ports in the module. The next step is the realization of the module itself. So since we are using a structural modeling style, we use gate primitives which are already defined in Verilog for realizing the model. So there are two gate primitives that are used in this example. The first is the XOR gate primitive. So there is an instance of XOR gate that is created in this model, and the instance name is X1. The instance name is used because whenever multiple copies of the same gate are used in a particular model, the different copies have to be distinguished. In the gate instance, the first port that is to be assigned is the output port, which is S out in the case of the XOR gate and C out in the case of the AND gate. The next two signal assignments are pertaining to the input ports A in and B in. So this completes the modeling of the particular module. The test bench is a portless entity. In the declarative part of the test bench, the signals which are going to be mapped onto the input and output ports of the device under test are declared. So there are two signals A in and B in which are declared to be of type reg. These signals will be mapped onto the input ports of the device under test. There are two signals S out and C out which have been declared as to be of wire signal type. Now the reg signal type is capable of holding a value. So the input signals which will be assigned logical values in the test bench are declared as reg. Whereas the signals S out and C out, which will be mapped onto the output ports of the half adder, are declared as wires because they will not be assigned any values on their own. They will be rather assuming the values which are driven to the ports by the device under test. In the second part of the test bench, that is the part consisting of the initial blocks, the inputs will be assigned logical values. So here I have shown two initial blocks. These are blocks of code which will execute in parallel. So the first initial block consists of a set of statements which assign different logical values to the input signal A in. Now the values which appear after the hash are basically delays. So initially A in is assigned to logic 0, and after a delay of 10 time units, A in is changed to logic 1. And after a delay of 30 time units, A in becomes logic 0. So you can notice that the time delay that is specified by the hash will be appended to the previous assignment. Likewise, the initial block which assigns the input signal B assigns a 1 in the beginning, and after a period of 15 time units it changes the logic value to 0, and after 45 time units it changes the value of B to logic 1, and so forth. The last part of the test bench is the part where the device under test is instantiated. So you can see, just as in the previous example of the half adder, there are three parts. The first part specifies the module that is to be instantiated, which is half add. The second part will be the instance label. Since we are having only one instance here, we are labeling it as HA1. And the third part consists of the signal mapping. So here we have used positional mapping. So the signal A in maps on to the port A in. Similarly, the signal B in maps on to the port B in, S out maps on to S out, and C out maps on to C out. Of course, here I have used the same name for the formal parameters, formal ports which have been declared in the module, and the actual signals which are assigned during the port mapping. But it is also possible to have different names for the ports and the actual signal which are assigned to these ports during the port mapping. So this completes the test benching process. Now the device under test can be simulated by using an HDL simulator, by running the test bench in the simulator. A small word of caution regarding the reg signal type. It has to be remembered that this signal type is not to be confused with a register or a flip-flop. The term reg simply means that this signal consists of a data structure in computer memory which can store a logic value for a specified duration of simulation time. Though a lot of free simulators for HDLs are available on the web, we would recommend the use of the ModelSim Ultra starter version, which is available in the link that is shown in this slide. Also, we have posted a video which shows how a code can be simulated using the Ultra ModelSim starter version.